predator-prey interaction is described by the Lotka-Volterra model, right here. Find the critical point in the first quadrant and use a numerical solver to sketch some population cycles. We're going to do this in MATLAB and then calcplot, and then estimate the period of the periodic solutions that are close to the critical point in part A. Okay, so the first thing I'm going to do is I'm going to go over to MATLAB, which I can't find right now. MATLAB is right here. I'm going to go over to MATLAB. And I made the window a little bit bigger so that we can see better. So I'm going to create a new section. Say this is chapter 11.4, exercise 10. And I'm going to clear all other outputs. Good. And now we're going to start doing stuff. So clear all old variables, clear all. Then defining new variables. That's going to be sims command x and y. So what do we want to do? Well, the first thing is we want to solve for the zero. So finding the zeros of the system. So we want the slopes to be 0, right? So we'll say that 0 has to be equal to negative 0.1 times x plus 0.02 times y times x times y. And then we have another one. 0 has to be equal to 0.2 times y minus 0.025 times x times y. All of that we want to solve for. So we'll put solve command. Close this. Here. It's saying that there's an error. Now, what we're going to do, that's the old y, that's why we want to clear all old variables. We're going to say that we're solving for x and y, and now we're going to put real and true because we want real solutions. And this is going to output into xsol and ysol, or you can call these as you want, as you please. So, right here, this is our first line command. And now we can see how many solutions we get. Let's see, control enter. We get 2 solutions. Now, one is at the origin, and they asked us the one that is in the first quadrant. So 8 and 5 is in the first quadrant. So we're just going to focus on that. So we're going to find the Jacobian, because this is a non-linear system because the dependent variables are multiplied together. And we're going to use that approximation to get some information out of the system. And the first thing that they wanted us to find is, well, we found the critical point in the first quadrant, and we want to use a numerical solver to sketch the population cycles. So let's first define the 2 right-hand sides of the equations as functions themselves. So p of x, y, for example. So defining the right-hand side for the Jacobian. And so for p of x, y, that's going to be equal to this. And for q of xy, that's going to be equal to this right here. Copy and paste. We close that. And we'll just leave it here for now. We're going to go back to Safari here. And now we're going to use calcplot. And I'm going to show you, I'm going to walk you through how to do this. So let's just refresh it. Okay, so get a new calcplot. Click on B, you get rid of the box. 3D mode, let's not put 3D mode. Let's click on here and put vector field here. Then we click down here on show differential equation systems of equation, restricted 2D view, and here we're going to write our Volterra model. So 0.1 times x plus 0.02 times x times y. And now this is 0.2 times y minus 0.025 times x times y. And actually in Calculate, you don't even need the times here. It just assumes that that's multiplication. And this is 0. That's why it's called a faceplane. Then we want to click on it. We want to use fixed lengths for all vectors. And let's maybe zoom out a little bit so that we include our other critical point. So to zoom out, we can do this. And, oh, it's too much. Okay, like this. Now, I think I want more vectors. I think I want 15 and 15. Okay, so now we can start seeing this. And now let's plot the critical points that we found. We know one is at 0, 0. Well, the other one, point right here, the other one, where was it? We said at 8, 5. So let's go and plot 8, 5, 0. We'll make this red. There it is right here. So now we see that this critical point it kind of looks like a circle, right? Well, let's see. If we want to animate it, maybe we want this to go all the way to 60. And see how it goes in a circle all around. And it seems like it doesn't fall. Let's say like 120. So see? And if we move this, it has a different rate, right? Okay, so that was interesting, right? So now we did part A. We found the critical point that is in the first quadrant. This is the first quadrant. This is the second, third, and fourth quadrant. And we used a numerical solver, in this case Calcplot, and we found some population cycles. So we sketched these, right? This is a population cycle. This is another. So what I'm going to do is go to part B. Estimate the period of the periodic solutions that are close to the critical point in part A. And to do that, we have to go back to MATLAB. We want to find the Jacobian first. And you do that with the command Jacobian. And then here you want to put your P and Q functions. And here you want to substitute your X and Y. And that's going to give you the generic Jacobian. Now I'm going to find the eigenvalues of the Jacobian evaluated at the critical point in the first quadrant, which is 8, 5. So 8, 5. So how do we do that? Well, we can use the subs command. We can say that J is the expression that we want to substitute our stuff in. Our old stuff is our X's and Y's, and our new stuff is our X sol 1, well, X sol 2, and Y sol 2. We want to substitute that in, and then we want to find the eigenvalues of that matrix. And you do that with the command eigen in parentheses. And we'll call this values simply. So we press Control Enter. And this is going to run the whole thing. This is the matrix. Now we find that that this is only imaginary. We have imaginary part, no real part. So it's going to be some sort of a circle, which kind of validates the graph here, right? And as we get closer, it should be closer and closer to a circle, right? And if I don't delete the objects, then I think I can make more than one trajectory. So I'm slowly learning. I still don't know how to get this to go fully curl variables, so I don't know how to get all the way to back to this point.